topic is Z prime search through ZH associate production at LHC.
Today I will talk about Z prime search through Z Higgs associated production at LHC. And this is based on recent work with my collaborators from China. First, the outline of my talk. First part is the motivation, and then I will give a brief introduction of the U1 prime gate symmetries and its associated Z prime gate boson. The third part is about the LHC signatures of PP to Z prime and then Z prime decays to Z and Higgs, and it's following 2 lepton, 2 jets final state. And finally, a summary will be given. First, the motivation of our work. Additional U1 prime gate symmetries and its associated Z prime gate boson are among the best motivated extensions of physics beyond sand model. A recently discovered 125 GeV sand model like Higgs attracts our interest to studying properties of the Higgs multiplier in this way. And if we study through the PP to Z prime and then Z prime to Z Higgs process, both Z prime to quark coupling and the Z prime Z Higgs coupling could be investigated simultaneously. Let's see first the U1 prime gate symmetries and its associated Z prime gate bosons. Generally, we have a SUN group, which it contains n-1 diagonal generators, which is corresponding to n-1 U1 groups. And specifically, if the theory is motivated from SO10 or E6 guts, it will break into sand model group times additional U1 primed groups. For example, if we consider E6 groups, it can be decomposed into SO10 times U1 symmetry, and SO10 can be further decomposed into SU5 and additional U1 symmetries. Here the SU5 can be written as a stand model, a part physics stand model group, which equals to SU3 times SU2 times U1y. Here, if we consider the U1 additional U1 prime symmetries here is greater than 1, then this additional Z primes will be produced. Here we collect the constraints of the Z prime mass from PP and PP bar colliders. The result is very model independent. So for the leptophobic Z prime, which the channel is Z prime to TT bar, from the CMS result with TT bar with following leptonic decay, the lower bound is 1.3 TeV. And from the atlas, they choose the hadronic decay search and excludes 2 ranges below 1 TeV and above 1 TeV. For sequential stand model, which means the Z prime coupling through stand model particles are the same as Z boson. With the channel chosen to be Z prime decays to left L plus, L minus, both atlas and CMS provide a lower bound of Z prime mass to be around 1.5 TeV, with lepton includes E and mu. From the both CDF and T0, the lower bound of Z prime mass is around 1 TeV. For the Z prime from left to right symmetric model, the lower bound is at 1 TeV. From the also we get these mass constraints of Z prime mass. They are very model dependent and parameter dependent. For example, if we change the search channel and the Burton ratio, then the mass constraints can be loosened to some extent. So in the following discussion, we will choose Z prime mass from hundreds of GeV to a few TeV. Then we consider how the Z prime couples to other particles. First, we review the standard model neutral current of Z prime, and we can write the standard model neutral current Lagrangian. Here, the G prime is the SU2 and U1 gauge couplings. With the definition of A and Z fields, we can transform the G3, G1 term into GEM and G1 term. Here the epsilon R is the chiral couplings of left-handed and right-handed. If we consider the additional Z prime with in the extension of the standard model to SU2 times U1Y and with additional U1 prime with n greater than 1, the new neutral current Lagrangian can be written in this way with the G alpha similar to the standard model neutral current. And here, when the n is equal to 0, it will reduce to the standard model case. Considering both the standard model Z and the additional Z prime together, we can write the Lagrangian of neutral currents of the Z prime to the standard model fermions specifically, and PR has the chiral coupling projections, and GLI is the chiral coupling of Z prime to fermions, and we know clearly how the GLR of Z to standard model couplings can be written, and we remain the GLR prime of Z prime coupling to standard model particle undefined. Here the Z prime decay width into fermions can be get from this Lagrangian, and as the light quarks, this is Z prime to light quarks decay width and Z prime to TT bar. C here is the color vectors for leptons and quarks. Then we consider the Z prime mediated vector Higgs interaction, which can be get from the kinetic terms of the Lagrangian. When we consider the Z prime mass is greater than the sum of Higgs mass and the Z mass, we can get the decay width of Z prime to Z Higgs. And here we can get the decay Burton ratio of Z prime versus Z prime mass, and the most largest contributions from the Z prime to QQ bar to lepton and also TT bar. Here Higgs with Z prime decays to Higgs Z occupies only 2%, but if we choose the Z prime to if we choose the Z here decays into L plus L minus, it will still serve as a good trigger at the collider search. So we consider how the Higgs then we consider the Higgs here. If we follow the 125 GeV standard model like Higgs, we can see from its production and its decay mode that in this figure we can see that the Higgs production association with vector boson, for example W and Z, and still plays an important role, and if we choose the Z prime, we consider Z prime here. Z prime mediated Z Higgs production will also contribute to these channels. And for 125 GeV standard Higgs, small like Higgs, the BP bar here will be the largest branch ratio. So in the following, we will consider the PP to Higgs with vector Z and with Higgs decay to BP bar. First, let's see the Z Higgs production at LHC. The specific process is the QQ bar to Z and Z prime, and with following Z associated with Higgs production, and we choose Z decay to tight leptons. The amplitude can be get, and the corresponding parameters of propagators can be found here. Here, NCNS is the color and speed vectors. Here's the production cross-section of this process. We choose Z prime mass from several hundred GeV to 2.5 TeV, and with different system of mass energies at LHC. This is for 7 TeV, 8 TeV, and also 14 TeV. For comparison, we also plot the Z-mediated ZH production and as a standard here. For the final state analysis, we define the final state 3 momentum of the total final state to be P, and the L minus star here is the lepton 3 momentum in the Z boson rest frame, and the angle between them can be get, and we then plot the angular distribution of charged lepton with different R. Here R is defined as the chiral couplings of Z prime to stand mode couplings. It's a ratio of left-hand coupling to right-hand coupling. And for the left-hand part, we choose the Z prime coupling to stand model particles is the same as Z coupling to stand model particles. And in this figure, the R here is increasing from 0.1, 0.5, and 1.5 with Z prime fixed to be 1.5 TeV. We can see that with larger R, charged leptons have that possibility to move against the Z prime boson direction. Then we can get the cross sections of this process, and the signal is PP to lepton and to jet final state. The main stand model background comes from Z Higgs, TT bar, ZW, Z2 jets, and WW2 jets. Among all these backgrounds, the TT bar background and also Z2 jet background is the dominant background. And from this preliminary result, you can see that kinematic cuts need to be imposed to suppress the stand mode background and to see the signal clearly. And here we also get the result of cross sections of different Z prime mass. And both of the results are for a center of mass energy of 14 TeV at LHC. How to choose the cuts to eliminate the stand model background? We here plot the transverse momentum distribution of different final state particles. Here is for the final state 2 jets, and this is for the final state 2 leptons. But here G1, G2, we define it as the G1 is the transverse momentum with larger is the jet with larger transverse momentum, and G2 is the with a smaller transverse momentum. And according to these distributions, we can choose the transverse momentum cut for jets and leptons as 300 GeV, 30 GeV, 100 GeV, and 50 GeV accordingly. And also, this is the minimal angular separation distribution for leptons, between leptons, jets, and between any leptons and jets. From this jets and leptons minimal angular separation distribution, we choose the delta R to be greater than 2. Another cut is from the invariant mass reconstruction. As the final state is 2 leptons and 2 jets, if we reconstruct if we get the invariant mass from 2 final state leptons, the MZ can be reconstructed, and if we choose the final state 2 jets, peak, resonant peak can be seen from the around the Higgs mass. And also, if we choose all the final state particles and do the invariant mass reconstruction, we can expect a peak around the MZ prime here. And so we choose the cut to be the invariant mass window here. All of the 3 situations, we choose the window to be less than 10% of the resonant peak mass. In the above discussion, the delta R here is defined from the horizontal angle and also the rapidity. The smearing delta, the energy smearing is performed according to this Gaussian distribution, and the AB is chosen for different values of leptons and jets. To further surprise the background, we try to use another parameter. We know that the Z prime has large mass hierarchy here from the Higgs and Z. So Z reconstructed from the final state change leptons should have a highly boosted Lorentz factor. So we demand that this factor should be greater than 3, which we serve as the third cut. After performing the 3 cuts, we can see again the total cross section of signal and background. We can see that after cut 1, cut 2, and cut 3 is all imposed, the all standard model background is clearly suppressed, and the signal remains clear, and also here for different Z prime mass, we also get the cross sections after 3 cuts. Then we can see the angular distribution that we defined before. After imposing cuts, its behavior is distorted to some extent, but it's also with larger R, the leptons tends to move against the direction of Z prime boosted direction. According to this angular distribution, we define a kind of symmetry, which is corresponding to the lepton, final state change leptons. We can see that both this angular distribution and this AFB is sensitive to R. We can we studied the cross sections of Z prime with different mass, and with in each situation with different R, and we can get their cross section, and for the kind of asymmetry accordingly, as the angular distribution is sensitive to R, and AFB also produce different values and behaves differently with R. And finally, in summary, motivated by the beyond standard model Z prime physics and 125 GeV standard model Higgs discovery, we investigate Z prime Z Higgs interaction with two lepton, two jet final states at LHC. Z prime two stand model forming couplings can be extracted from the left-handed and right-handed couplings, and the ratio R can serve as an important parameter to specify various models. The stand model backgrounds are estimated and efficiently surprised by the kinematic cuts of our chosen signal, and corresponding to angular distribution of charge leptons, a kind of asymmetry is defined and turned out to be sensitive to R. Different new physics models that predict Z prime, they have different Carroll couplings, which is related to R. So this distribution and asymmetry can help to understand this interaction of Z prime to ZH, and also serve as an attempt to distinguish between different models.
So other questions for Dr. Zheng?
Yes, in looking for the Z Higgs signal, there's a lot of background initial state radiation getting into your Higgs jet. And I wonder if you've tried some kind of subjet analysis, pruning, or something like that to clean it up so that you get a sharper Higgs mass. Did you do that?
You mean different...
There's various kinds of ways to take apart a jet and try to remove low momentum particles that are not really part of the Higgs decay, and then you'll get a sharper mass.
You mean the transverse momentum cut?
Not a simple cut. It's like in a paper that I mentioned, I talked of PDRNS.
Oh, I guess we didn't try that.
You might find that you get a better signal in the background.
Okay, I'll check that. Thank you.
So, I should have a quick question. So, since you finished well ahead of time, you actually have the optimization of selections. What's the figure of merit you optimize on? So you have optimized a set of cuts for. Maybe you can go back to the first few slides.
Transverse momentum distribution and minimal angular separation.
So what's the figure of merit you optimize on?
You mean the background?
How did you optimize these cuts?
We just choose this cut of these values, for example, PT greater than 30 GeV, and we just input it to the program.
Okay, so it's not based on signal over square root of signal plus background or some other figure of merit. It was chosen by eye first, or?
You can always get the transverse momentum distribution, and then you require it to be greater than some value, so the cross section will be reduced.